So let's now go through the derivation of the Euler equation. Okay, so we start off with this statement of the problem. So you're given this function, big F, and big F depends on x, but it also depends on y and y primed. So y is itself a function of x, and y primed is just the derivative dy by dx. So you're given an integral where the whole integrand depends on x explicitly, but it also depends on y and y primed. Both of these depend on x. So this whole integrand is just a big function of x. Okay, got that? Because y and therefore the derivative y primed both depend on x. The entire integrand is just a big function of x. And let's say we integrate that function between x1 and x2. Okay, so you're given big F, but you're not given y. You don't know what the function y of x is, therefore you don't know what y primed is either. So let's say when you do this calculation, when you do this integral, if you did happen to know what y was as a function of x, you calculate this integral, it is a definite integral, so your answer to this integral is a single number, okay? And let's say what you want to do is to find find the function y of x that will minimize or maximize this definite integral, okay? So that's the statement of the problem. So what we're going to do, as we said, is to derive something called the Euler equation. And what the Euler equation is a differential equation. And the differential equation has a solution, y of x, which is the same function which is the answer to this problem here, namely, what is the function which minimizes or maximizes this integral? Okay? So we're looking for an unknown function here, but that's exactly the same thing you are looking for in a differential equation. You're told this function satisfies an equation, determine what that function is. Okay. So let's say we have this information. So here's an illustration. I posted this figure in the on the Moodle site for the page. So here's point 1, so at value x1 and value y1. I say that again. At value x1 and x2, those are the x values of the two points that we are given. So you're given this information, what the values of these points are. So that means you'll also know what y is for each one of these 2 points. And then there's a function which connects these 2 points. Maybe it's the blue function, or maybe it's something else. Okay, but if we're looking for y of x, remember this is the function that will minimize or maximize this integral. Okay, so let's say it is this blue function. Okay, so we don't know what it is yet. But let's introduce another family of functions, call it big Y. So this blue one is little y, the red one is big Y. And we're going to define big Y, which is a function of x, will be equal to little y of x plus a quantity epsilon times a function eta of x. So this is the Greek symbol eta. It's a function of x. Okay? Eta can be anything you want it to be, except we insist that eta at x1 and x2 be equal to 0. And if you think about what this means, it means regardless of epsilon, big Y will be equal to little y at x1 and x2, because that's where eta is equal to 0. Okay, so you can visualize it this way. If little y is the blue curve and big Y is a red curve, the difference between them is epsilon times eta, and eta is equal to 0 at x1 and x2, so obviously that means big Y is equal to little y at point 1 at value x1 and at point 2 at value x2. Okay? And here's another kind of trivially obvious point. If I take the derivative of this equation, then I get y, big Y primed is equal to little y primed plus epsilon, which is just a number, a parameter, multiplied by the derivative eta primed, d eta by dx. Okay, so the equations that follow in these slides are just the same equations. We've already said that we're choosing eta to be 0 at the two endpoints, and that of course means big Y equals little y at x1 and x2. Okay, but otherwise eta is an arbitrary function. Okay, and I've also said big Y primed is equal to little y primed plus epsilon times eta primed. Now note that when the parameter epsilon is equal to 0, big Y is equal to little y. Okay, that's trivially obvious just from equation 4.7. When epsilon is equal to 0, big Y is equal to little y at all values of x, not just at x1 and x2. Okay, so let's remember that. When epsilon is equal to 0, big Y is equal to little y. That, of course, is the desired function. Little y is the function that is going to either minimize or maximize this integral. Okay? So let's consider a modified integral. So we have the integral back here, right, where the integrand is the big f function is a function of x, y, and y primed. Let's replace little y and little y primed with big Y and big Y primed. Now it's not going to be the same integral. It'll be something else because generally big Y is different from little y. Okay? Now, whatever this integral is, first of all, we note again that the integrand is just a function of x. It depends explicitly on x, but also implicitly on x because big Y and big Y primed both depend on x. So this is just a function of x, and we're going to integrate it between x1 and x2. Okay? Now, remember, big Y, of course, depends on epsilon. So epsilon is this arbitrary parameter that we still have. So when we evaluate this integral, okay, we will get a quantity, a single number, but it will depend on this value of epsilon, which is completely arbitrary. Okay? So the integral will depend on epsilon. And the left side of this integral equation is just the integral is a function of epsilon. And if I want to minimize or maximize this integral, oh, I think I know how to do that. Now I can just borrow from regular calculus. I'll take the derivative di by d epsilon and set it equal to 0. Well, where is it going to be equal to 0? When epsilon is equal to 0. Because when epsilon is equal to 0, big Y is equal to little y. Okay, you might need to replay this screencast and look at your notes to follow that logic. But basically, to solve our problem, we're going to take this integral, which depends on epsilon, take that derivative of this integral, of this function, set it equal to 0, and insist this be true at epsilon equals 0. Then that means the integral will be an extremum when epsilon is equal to 0, therefore when big Y is equal to little y. And little y is our unknown function that we're trying to find. Okay, now let's take the derivative of this integral. F depends on x, and y primed. Epsilon is hiding in there. Now it's not hiding in the x, but it is hiding in the y, and big Y primed. So if I take this derivative, this differentiation operation, and I bring it inside the integral, I want to differentiate the integrand, big F, with respect to epsilon. Now, big F depends, in addition to x, it depends on big Y, and big Y depends on epsilon. So the derivative of big F with respect to epsilon will be, using just the chain rule of calculus, df by d big Y, and that's a partial derivative, you'll note, multiplied by d big Y by d epsilon. We're going to treat y and y primed as basically independent variables here. Okay, so that means using the basic result of multivariate calculus for the chain rule, that we have a second term, df by dy primed, multiplied by dy primed, d epsilon. Again, note that this is a partial derivative because big F is a multivariate function of x, y, and y primed. Okay? So again, you might need to go through this part of the screencast a couple times, but I think you'll find when you do so, it is relatively straightforward. Okay, but you might need to think about it for a little bit before you get it. So continuing on, let me just borrow this figure over here. Let's see here. D big Y by d epsilon is simply equal to eta of x. Okay, and that's what we have here. But dy primed by d epsilon, that's this. If you take the derivative with respect to epsilon, I only see an epsilon here. That derivative is clearly eta primed. Okay? So let's make that substitution into equation 4.13. So what goes here is eta. What goes here is eta primed. So with that substitution, we get equation 4.15. Now, we have two terms now because of the chain rule for a multivariate function. We had two terms back in equation 13. It's carried over into equation 15. I'm going to leave the first term and just consider the second term. So I could break this up into two integrals, so the second term will give me a second integral. And that second integral that goes with the second term looks like this. And we're going to use integration by parts. So if you follow the logic here, okay, this derivative multiplied by eta primed, which itself is a derivative between x1 and x2, is equal to, well, that same quantity, df by dy primed, times eta x, evaluated between those 2 points, minus the integral between the same two bounds of the derivative with respect to x of d big F by d big Y primed multiplied by, well, we had an eta primed, a derivative. Integration by parts, the recipe tells you you should have not the derivative of the function, but the original function. Okay? So you might need to just write down, the u dv integral is equal to uv minus v times du. Choose u and dv appropriately. This is what you get.